Good morning, afternoon, or night to everybody. It's a pleasure for me to introduce in few minutes this session. I am Carmen Andrade from the International Center for Numerical Methods in Engineering in Madrid, Spain. And I am here on behalf of the convener of Commission 8, that is Jose Matos, is our convener. And there are deputy conveners Manu Sanzanam and myself. Commission 8 has this structure. In this moment, we have only 4 task groups or working groups active. One led by Steinar Helland on, we say, common approaches because it's a mixture of different aspects, and we have there several working parties. Those active are in black letters, that is on durability planning, on the classification of exposure zones. Also those were chaired by Rodney Pauli or by Juanita Nagula. Another one on eco-efficient concrete that is led by Stephanie von Grief-Dirfel, and a final one on the durability and serviceability and ultimate limit state that is chaired by Robbie Caspil. There is the task group 8.9 that I will present next because I am chairing, I am the responsible. There is one that we name 8.12 that is on deterioration mechanisms related to other phenomena than corrosion, that is chaired by Manu Sanzanam, and that has different working parties on freeze and thaw, abrasion, chemical attack or internal attacks, with Proni Suraneni or Michael Vogel, Alexandra Bertrand and Farsad Rajibiopur as the leading people, and a final one on testing and monitoring that is chaired by Carola Edvardsson, and that we have 2 active working parties, one on testing all concrete by Roberto Torrent and one on monitoring chaired by Joan Ramon Casas. This webinar is held under the task group 8.9 that I am chairing together with Josh Gulikers, that we are dealing with deterioration mechanisms related to corrosion. And we have 5 working parties that they are active. One on the initiation period, chaired by Amir Rahimi, the propagation period that I directly chair, the chloride threshold that are the responsible organizing this workshop today, and the corrosion in fiber reinforced concrete by David Gardiner, and corrosion in pre-stressing by Brett Pilstick. This is our organization and the active groups. I have no more to say that the present workshop that will be introduced later by Frank Papworth and Federica Lolini, that are the responsible of the subject, is this activity is part of our activity because we thought that it will be very good to listen and to discuss among several specialists which is the state of the art in the subject of chloride threshold. Well, I wish you a nice workshop, and I just leave my screen for Frank Papworth.
Good day, everyone. I use good day advisedly because it's different times in different parts of the world. I'm going to be talking to you about a bulletin that we have started to produce. And I will start by describing that. It's on the critical chloride content of concrete. The objectives of the bulletin were to give clear guidance on the use of CC, critical chloride level. The bulletin will in fact review the research on critical chloride, and there is an absolute abundance going back over 50 years. We're very fortunate that Early Angst has done a great job over the last probably 5 to 10 years of reviewing a lot of that information, and his latest paper was published in 2022. He will be on the committee and will provide invaluable input on that. One of the things, or the main things that this document wanted to address was the extension of the critical chloride level from the current version, one single version in Bulletin 34, FIB Bulletin 34, to try and tighten it down for different exposures and what have you. So there's a list there of the different things that we wanted to have chloride, critical chloride distributions for. Apart from identifying these things, we also wanted to prefer to provide what research was still needed. And I think that will tie in together with new and better models over the next decade. So far, we haven't had a committee meeting for this working party. We do have a draft document, an incomplete draft document, I should say, which we want the committee to review and help build up. And anybody prepared to join that committee should contact Federica. First of all, then, what is CC, the critical chloride level? It's essentially the, as we probably all know, it's the level at which steel might start to corrode. For many years in the early days, back in the 70s, a lot of people were using a single value. These days, we pretty much all use a distribution for the critical chloride level, and it's quite a wide distribution. There's quite a number of things which will be in the bulletin, which I won't be discussing here. They're listed there. It's just not enough time to go through them all. They will be reviewed in some detail in the bulletin based on previous reviews in the main, and there's several major reviews that have been done. It's quite interesting looking back at the history. The common value for CC is 0.4 weight percent of cement. But I look in the 70s, 80s, and even the 90s, there was never really any stochastic value put on it. It was just a value quoted of 0.4. And very often I couldn't determine whether the people were quoting a characteristic value or a mean value. So we need to be careful when we look at some of these old texts and compare them with more modern data. Bulletin 34 was published a distribution, and here we can see the distribution with a mean value of 0.6, a standard deviation of 0.15, and limits to the skewed distribution. And that's how the CC is defined in the Bulletin 34. I did try and find where that came from, but it's unreferenced. But we assume that Bulletin 34 in general came from the Ccrit project, so assume it came from there. This value for the mean of 0.6 is consistent with a CC value based on as a characteristic value of 5% probability. There is no CC in Model Code 2010 or in ISO 16204. FIB Bulletin 76 uses the same CC distribution as Bulletin 34, and that is referenced back to Gellon in 2000 paper, probability-based service life design. I have had some communication with Uli Angst, and he's actually quite critical of this, saying that how are we basing, FIB basing the critical chloride level on one person's research rather than the multitude of data that's out there, and that is certainly something we need to look at. We also think there should be some guidance on how to limit the use of CC in Model Code 2020. Why is it important? Why is it important to know more about CC? Well, sustainability is becoming ever more important, and that's going to drive the need for more durable structures and more efficient use of materials. And having a good model and a great understanding of CC is essential if we're going to benefit from that. So CC values will drive the use of these materials because we know how to use them, and we will know how durable they will be. So huge potential savings on whole of life costs, So in my opinion, because there is still such consternation, as we'll see, about what the CC values distribution should be, research funding for the CC value and modelling would reap huge global rewards in the future. And we'll get some inkling of that. The fickleness of CC. It was interesting, and we will hear from our next speaker about his experiences with high chlorides and no corrosion. But going back to 1973 with Stratford on bridge decks, he looked at the critical chloride level for 15 to 25 MPa concrete. So this is concrete of very low quality, if you like. And that's also an issue we need to bear in mind, that people are developing CC values for very different quality bands of concrete, and we shouldn't be mixing them up. What he recorded was that the chloride level determined whether the steel went from passive to active, but he found there were certainly lots of cases where the steel had become active, but there was no visible corrosion, which is interesting in that it tells us that visual assessment is probably not the right way for assessing CC values. He also noted that the actual rust that occurred depended mainly on the moisture contents. He found no corrosion in cases where there were massive salts, unless there was sufficient moisture. And he came to the conclusion that a prerequisite level for chlorides for bridge deck corrosion was 0.32% by weight of cement, but pointed out there's no corrosion at very high level chlorides. So CC is expressed as a distribution for full probabilistic analysis, but wasn't considered as a distribution generally until the 1990s. Already mentioned that. In the 1970s, then it was suggested, based on this early research, such as Stratford's, that that there were three main prerequisites for corrosion: chloride threshold at the reinforcement, voids around the reinforcement. And when we talk about voids, you might be thinking of honeycombing, but we're really actually talking about much smaller voids in terms of this corrosion. And we should, in fact, just exclude honeycombing, large bleed defects, etc., from our analysis of CC altogether, because we just shouldn't permit those things. And the concrete within a certain moisture range was necessary. Low moisture contents, high resistivity, no corrosion. That might be irrelevant for chlorides. It's a fact. And saturated concrete has voids filled with high pH water, which is important. I'm not going to go into this. Why CC varies so much. Angst went through it in detail. That's a summary of some of his research, and his conclusions are basically say the variation of CC is affected by the steel, the interface, and the concrete. He believes you can't base CC just on the concrete. So if we have this wide distribution, which is unsatisfactory, are there some key influences that we can add and give new distributions for, but actually hone down on what those distributions are, make them narrower distributions, more distributions which are narrower? Well, I decided I'd have a look at the FIB distribution. This is pretty much the FIB distribution, 0.6 mean with a standard deviation. But I created that by just creating arbitrarily a load of critical chloride values, which would give me that distribution. My concern was that, in fact, that wide distribution of FIB was made up of distributions of low quality, moderate quality, and high quality concrete. And I wondered what would happen if I modeled those different concrete qualities. So you can see here, I've got the mean critical chloride level, standard deviation, characteristic values, and these low quality concretes, etc., low, medium, and high quality, were created from exactly the same data that created this curve for FIB. If I just took all the data from these three curves, I would get this one. So it's just splitting the data up for the different structures. And you end up, when I split them up, now I have to accept that that's arbitrary, that you could end up with poor concrete with a critical chloride level of 0.38, and high quality concrete with a critical chloride of 0.71. At that point, I decided I would compare it with research. This goes Rick Pedersen's data, which was from 1996, where for everything kept the same except water binder ratio. He measured the chloride threshold, and he found that water binder ratio probably affects the voids, which affects the chloride threshold. And what he found was a water cement range, for a water cement ratio range of 0.5 to 0.32, critical chloride range from 0.4 to 1. Okay, so I then looked up, did some calculations on what the reliability at 50 years was. So if I took my curve from FIB, critical chloride content, and did my analysis for the low quality structure without knowing it was low quality, I would say it was fine with a reliability of 1.5 if it had the required cover of 70 millimeters. However, if I'd actually picked a low quality structure without knowing it, I would have actually needed a cover of 80 millimeters to give me my reliability of 1.5. And so what this points to is that if we use a very wide distribution of FIB, we may be underestimating the performance of high quality structures and overestimating the performance of low quality structures, which could be quite dangerous. I also just did the one where if critical chloride level was high, up around 1, and I note that Papworth has done modelling based on such a high critical chloride level, then you can see that my cover requirement drops very significantly from what the FIB requirement would currently be, showing that there can be some great economies. Well, that's all very well. I can relate chloride threshold maybe in the first instance to water binder ratio, but Kathler, who works with angst, has come up with a paper suggesting a drive for a test to measure project-specific CC so that we can measure all of the factors which are affecting our specific structure. I won't go dwell on this. It's because somebody's going to give a talk on this particular aspect, the critical chloride level for a structure. I'll just make the point that it's interesting. This is your FIB distribution for critical chloride. This was the distribution for a particular structure, and they're not so far different. So we do need to bear in mind that even on one structure, the variability is quite high, can be quite high. So what value for CC in atmospheric zones? Angst says need more but narrow distribution. What factors will yield a significant improvement in the outcomes? That's one of the things that the bulletin needs to get down into more detail on. We have a currently agreed distribution in FIB Model Code Service Life Design, very, very broad, and we really do need to apply some limits to that, such as the other prerequisites that I talked about, and the reasons why we discussed that. I would love to be able to give you more distribution based on water cement ratio, but that's going to take some discussion and review of the data. Now I'd like to briefly look at immersed concrete samples. And this is a test which I think Harrison did in 2014, but it was based on work by others, where you take water samples with different chloride contents, and in some you put in some cement. And what you find is that in seawater with no cement, you've got corrosion. In seawater with a bit of cement and 10% chlorides, you didn't get corrosion because of the cement. And even at very high salt concentrations, you still didn't get corrosion. And what that's pointing to, that is, if we have saturated concrete with voids filled with water, which will leach the hydroxides in the concrete, you will have high pH. And therefore, it's not surprising maybe that we don't get corrosion in the underwater zone, because the critical chloride level will be very, very high. This was some early work I did on Tungstan's Tower, where we took cores from the underwater zone, and we found that there was no observed corrosion at the reinforcement depth where the chloride levels are at 1.4, which just tends to be supportive, and there's other data which is supportive of that. Sandberg found the critical chloride level for the immersed zone was 2.1. So we can start to say that maybe we can set up This is our critical chloride level for normal black steel in the atmospheric zone. Then maybe we should be using this curve for the immersed zone. That was found by Esquerdo. In fact, maybe it's a tighter distribution than he found. We'll have to look at that. I won't dwell on stainless steel, just to say that I don't think it's appropriate to use the stainless steel as an avoidance measure without really understanding when it might corrode and what different stainless steels might do. So we should develop critical chloride levels for stainless steel. Similarly, for galvanized reinforcement, this isn't being talked about, but Lalini's paper, so you can ask her questions about this, and came up with a mean value of 1.2 for the critical chloride level for galvanized steel. I won't dwell on this either, just to say that I did go to a conference in Portugal on corrosion of steel, and they were talking about reinforcement corrosion, and were horrified when I suggested using hot dip galvanized bars in coastal environments where there's chlorides. And I think that all stems from some early US lab testing showing a very low value for CC, but it was accelerated testing, and ultimately that was proven wrong, and HDG is now accepted. And I think we're considering this beta distribution for galvanized steel. Just important to understand why. I've looked at coastal structures and marine structures, black steel and galvanized steel. So this is a typical mix, if you like, for coastal, typical mix for marine, and put in the critical chloride contents for both. And you can see that the cover for 50 years to depassivation went from 50 years to less than 20 by using galvanized steel. The marine structures from greater than 75 for black steel to 50 for galvanized. So great economies can be made there, which is good for sustainable and bottom dollar. And I've seen myself how you can save millions of dollars on large bridge structures by using low covers when the mixes and everything is properly designed. The last one is looking at steel fibers. This is some work by David Gardner of SMEC, where the brine outfall tunnels, 2 times normal seawater level, precast segments were made using steel fibers. He was clever enough to put in some samples that he could test subsequently, and what he found was, I've forgotten what age this is, I think it was about 9 years. He found that there was no fiber corrosion past 2 millimeters, suggesting, based on the chloride profiles here at 2 mil, that at 2.8% weight percent of cement, they had no corrosion. Based on that work and other work, we might suggest then that for steel fibers, you use a 3% by weight of cement as your mean critical chloride level, and you design a sacrificial layer for your concrete based on the initiation depth in the design life using this critical chloride level. I won't worry about too much about this. It's just looking at what reliability values you might use for different situations using steel fibers. In my conclusion then, is use of CC currently viable? I will quote Angst, as I promised him I would. He says, it is an illusion that Ccrit can be predicted on the basis of mixed proportions. Ccrit will always be the result of the entire steel concrete interfacial system and the exposure conditions. And I agree with that. All the research shows that. However, I believe that we sometimes overlook small improvements, if you like, and that using CC and modeling is already a better approach than deemed to satisfy, because it does enable you to vary certain things once you've calibrated your model. So I think it's already better, but we need to go further. These are possible approaches which I've described to you. Already, I think the literature might lead us to suggest these different values for different qualities. And if we started to break the literature down on these, it might enable us to look at other factors that might be prerequisites or might be adjustments to these. So that's the summary of what I've currently proposed should be used for critical chloride levels in design, but obviously we're looking to go further. Thanks.
Thank you, Frank. I have a, well, I will address in my presentation, but I don't agree that it is in the 90s when the distributions appear, because Hausmann, that was the first proposing a chloride threshold in 1967, he proposed a distribution already.
Okay.
Okay, we will comment on there. If not, there are not other, we can go.
As you were around at the time, Carmen, would you agree that in the 70s and 80s, a lot of people were quoting critical chloride levels without saying whether they were characteristic or mean values?
Well, I will address in my presentation, but the people try to obtain the chloride threshold, and it is the different techniques and the different definition that is the basis of the discrepancies. In fact,
Okay.
well, I had I was fortunate enough to meet Hausmann in a congress, and he explained to me what he did, and that is why I started to make a statistical study, because you need to have several identical specimens for having the statistical distribution. But
Absolutely.
the people was communicating the chloride threshold that he found depending on the technique, whether it's natural or it's a polarization curve or whatever. And what is that? You cannot say if you don't have at least 10 samples identical to say if it is the mean or if it is the characteristic. And what is true is that there are not statistical studies. I think that apart, well, I will say later. First, I don't follow now. Thank you. But that the characteristic of the also uh, depends on how you interpret the technique that you use to obtain the value on the chloride threshold. Okay. I don't know if you are satisfied with my question, or you would like to comment further, but maybe in the discussion at the end, if we
Well, I think the whole thing, I mean, it'd be good to talk about it after your presentation, but it's certainly very clear that there's a huge amount of data out there, but people are using different materials, different steels, different construction methods. They're using lab samples, field samples, potential methods, visual methods. You know, it really takes, we've got so much data, it's very difficult to sort it out.
Yeah. No, but I will present in my presentation. You can treat in a comprehensive manner.
Yeah.
I think that there is a way to overcome that. I don't agree with the last paper of Welly Ernst, in the sense that, of course, as all the properties change with the particular structure, the strength and so, but the engineers are able to handle it. I mean, we need to be able to handle the chloride threshold and just to find the way how to, for an engineering application. And I think that the engineering application is what is needed to be in FIB, to be agreed and to be published. Okay, in that case, many thanks for your presentation.